ligand being a substituted ethylene diamine molecule. Specifically, the ethylene diamine molecule in question had an optically active nitrogen donor atom. So to decide whether or not this thing is optically active, the complex of such, requires you to look past the symmetry of the complex itself. Because if the ligand donor atom is optically active, then any complex you make of this stuff is by default optically active. The answer, however, I wrote was written when I overlooked this consideration. So I've got a statement that for the trans version of the complex containing the substituted ethylene diamine with an optically active donor nitrogen atom, I said the complex is not optical, not optically active. That's wrong. So if you've looked at that, please take note. Now, let's get at the remaining considerations, which again, some of you likely have already been over at least one time by way of last Thursday's discussion gathering. But just to be sure. We finished yesterday by paying attention to the fact that ethylene diamine is a somewhat better ligand than the ammonia molecule. Not just because ethylene diamine is a chelator, or as ammonia is monodentate, but also because the nitrogen donor atoms for ethylene diamine are somewhat better Lewis bases than the nitrogen in ammonia. And we pointed out that if you try to determine the difference in Lewis base or Bronsted base strength of ammonia versus ethylene diamine on the basis of atomic electronegativity, you'll reach the wrong conclusion. Because carbon has a higher atomic electronegativity than hydrogen. But the upshot of this is again to realize the chemistry of a bound atom may well be considerably different from the chemistry of the atom when it's not bound. And for the most part, we are concerned with the chemistry of atoms in the bound state. So in this case, as we pointed out, to rationalize why the nitrogen donor atoms for ethylene diamine are somewhat better donor atoms than the ammonia nitrogen requires orbital electronegativity assessment. Carbon for ethylene diamine is sp3, whereas hydrogen cannot possibly be a hybridized species, because hydrogen has a max electron capacity of 2 electrons and can only participate in bonding from an orbital interaction standpoint by use of its 1s orbital. And we recognize electron density is certainly more stable in a 1s orbital than it is in an sp3 hybrid. From an orbital electronegativity standpoint, applied to hybrid orbitals, as we've noticed, the greater the s character of a hybrid, the greater the orbital electronegativity of that hybrid. Upshot, from an orbital electronegativity standpoint, hydrogen stabilizes electron density better than an sp3 carbon. From this we can recognize why the electron density on the nitrogen donor atom for ethylene diamine is somewhat more reactive, somewhat less stabilized compared to the electron density associated with the non-bonding pair on the nitrogen atom for ammonia. That accounts for the somewhat greater donor atom character of the ethylene diamine nitrogens. You'll take a look at this stuff in organic class, for those of you who go there, in terms of, as the organic chemist will refer to such, primary, secondary, and tertiary carbons. A primary carbon is a carbon that's bound to one other sp3 carbon and two hydrogen atoms. Secondary carbon, bound to two sp3 carbons and a hydrogen atom. Tertiary carbon is bound to three sp3 carbons, like this stuff, with this being a carbon atom. You'll find out that for carbon, this was carbon, with three methyl groups connected to it, and a hydrogen atom connected to this central carbon atom. If that stuff loses H as H plus relative to one methyl group or two methyl groups with the other bound peripheral species being hydrogen atoms, losing H as H plus, you'll find out that when you have the three methyl groups bound to the carbon, H plus loss by the carbon, the central carbon, is most difficult because the methyl groups are electron releasing relative to hydrogen, which is what we're talking about here. So, if these methyl groups are electron releasing, to try to place a negative charge on the carbon from which H left as H plus is most difficult, because that negative charge is now most concentrated. For example, parallel case. How about this as a Lewis base or Bronsted base compared to ammonia? This is immediate parallel to what we've just been talking about. How do you think the Bronsted base strength of ammonia compares to the Bronsted base strength of this? Which of these is the better Bronsted base? This thing, because these methyl groups are electron releasing relative to hydrogen. That's what this orbital electronegativity analysis has shown us. So Kb for this, bigger than Kb for this. Kb for this, bigger than Kb for ethylene diamine. Because ethylene diamine nitrogen have two hydrogen atoms and an sp3 carbon bound to such. Here, this nitrogen just has sp3 carbons bound to it. All electron releasing carbons relative to hydrogen. So again, this analysis, among other things, reminds us about the importance of paying attention to the chemistry of an atom when it's in the bound state. That's what counts. Nitrogen bound to methyl groups rather than nitrogen bound to hydrogen. All right, enough on that. We go to ring stability and ring strain. You should know something about ring strain. I can take a look at these papers at a glance and see what you've learned about ring strain. In a nutshell, the smallest possible ring that you can consider forming is three atoms, three members, three atomic members, which would give you a triangular shape species. and planar because 3 points are always containable in a plane. This stuff you will find in organic class, which contains a 3-atom ring. 2 carbon atoms and 1 oxygen atom in the ring. This stuff is known as an epoxide. That's the organic chemist's name for an ether which contains 2 carbon, 1 oxygen, 3-atom ring. We don't care about the fact that these are epoxides, at least not at this stage of the game. So I didn't write that down. I don't care about the name of this stuff. What counts is to realize that this stuff is damned reactive because this ring is damned unstable. This ring has a great tendency to break up the ring. Upshot regarding coordination chemistry for transition metals is if we imagine the metal ion is at this corner of this triangle, and these are donor atoms, like for this molecule. Name is hydrazine. Clearly, if hydrazine behaves as a chelate, I get a 3-atom ring. But this ring is not formable. It's too reactive. It's too unstable. Why not? Well, I trust you learned in 2045 that the strongest possible sigma bond results when the electron density for the bond, the shared electron pair, is positioned where relative to the nuclei of the connected atoms. If my fist is an atom nucleus and this fist is an atom nucleus, and these atoms meet with each other to make a single bond, a sigma bond, where should the shared electron pair be relative to these nuclei positions for the shared electron pair to be most stable, giving you the strongest bond? Should this electron pair be up here? Down here? Over here? Where should it be? It should be right between these nuclei, because when the electron pair is right between the nuclei, it's stabilized to the greatest extent because when it's right between the nuclei, it is mutually as close as it can possibly be to both nuclei. That's it. Well, you can't achieve that with rings like this. Why not? Because if you had a shared electron pair here for the sigma bond between these atoms, and another shared electron pair here for the sigma bond between these atoms, I'm sure you've seen this diagrammatic representation of electron pair previously. These electron pairs are only apart from each other by 60 degrees. They're too close to each other from a Coulombic stability standpoint. They repel each other quite strongly. Upshot, these electron pairs wind up being here and here, rather than here and here. That leads to appreciable bond weakening. You get the same kind of effect if you try to form a 4-membered ring. I think there might be a couple of known examples of stable 4-member chelate rings, but in general, they're not formable. So we'll stick with the in general part. If we treat this as a planar entity, how many degrees are encapsulated inside this planar entity? How many? 360. 180. 360. So if we treat this as a perfect square, the bond angles would all be 90 degrees, including the bond angle where we'd find the metal ion if with this type of chelate we made an octahedral complex, which would give us something like this. M for the metal ion, and this stuff 3. And here the charge on the iron would be the same as the charge in the middle line. Okay. That would be the composition of the octahedral complex, or a complex was generally octahedral in shape. If this thing was capable of behaving as a chelating ligand to give stable rings. But can form such species. Well, if we consider this as a chelating ligand, methylene diamine. Again, I don't care about its name. And by the way, you can't even make this stuff, but we can still write its formula on the board and talk about it. We can talk about the chemistry that we would expect this to exhibit if it existed. Carbon is sp3. The nitrogens are sp3. What are the so-called preferred bond angles for sp3 hybridization? 109.5 degrees. Neglecting other factors like non-bonding pair, bonding pair, repulsion interactions, and things of that nature. Well, if this is a perfect square, what kind of bond angles do we have? Or if this is simply a planar surface with 1, 2, 3, 4 angles, we'd have 90 degrees. Well, that's almost 20 degrees short of the preferred bond angles. So again, we'd have a case where the bonding electron density wouldn't be immediately between the nuclei of the connected atoms, because there'd be too much repulsion among and between these bonding electron pairs. So you get weak bonds as a result. Now let's go to ethylene diamine, which we know forms stable chelate rings. Again, I remind you that ethylene diamine is the best known chelating ligand, likely because it's the simplest. Here, we have a chelate ring with 5 atomic members. And when I put on my famous Easter hat, I told you, count the number of atoms in the ring, because it relates directly to this issue. 5 ring atoms when you add in the metal ion. Each of these atoms, skeletal atoms, is sp3 hybridized. So with that, I showed you the model, and recognizing that these skeletal atoms are all sp3 hybridized causes you to recognize that regardless of how textbooks type formulas and how I write formulas on the board, or how you may write formulas on your notebook paper, this is not a linear molecule by any stretch of the imagination. But because of free rotation along the skeletal atom single bonds, well, all single bonds, nothing but single bonds on this, we can wind up with a geometric orientation for this molecule, ethylene diamine, which allows its non-bonding electron density from the 2 donor nitrogen atoms to aim at the same place in space, and then I get my famous Easter bonnet. Now, tell me, if we treat this 5-membered ring as being planar, flat, how many total degrees in here? How many total degrees in here? Well, let's write it up here. 540 if planar. Degrees contained within. You must have learned in plane geometry class. Now, when you talk about planar polygons, every time you add an angle to the polygon, how many contained degrees are you adding? 180. 180, 360, 540, and then in a moment we'll talk about this with 720 degrees if we treat this as a planar figure. All right? Now then, sp3, 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 sp3. So these are all looking for bond angles on the order of 109.5 degrees. But if this thing engages in forming an octahedral complex, which we know it does, then the bond angle where we find the coordinated metal line is 90 degrees. So I drew this. So if we treat this as 540, We got 540 total minus 90 for the bond angle where the coordinated metal line is located, divided by 4 remaining bond angles. 1, 2, 3, 4. Now watch out. This is pretty damn tough arithmetic. What's that equal? 112.5. Now that's a little bigger than 109.5 degrees. So now we'd have bond angles which are somewhat too large, or is that true? Will we instead have the desired bond angles? Well, go back, please, and recognize that this chelate ring with ethylene diamine is or is not planar. It's not planar. Well, all these component atoms of this ring don't lie in the same plane. I'll turn this way so you can get a side-on view of me wearing my Easter bonnet. Well, tell me, when you deviate from planarity, what does that do to bond angles? Does that keep bond angles the same? Does it make bond angles get larger? Does it make bond angles get smaller? Imagine that my two hands, which are each holding this piece of paper, are connected by the piece of paper. The piece of paper is a bond, or is a series of bonds going across here, connecting my hands. Be a bunch of sp3, pardon me, a bunch of sp hybridized atoms, right? Because for sp hybridization we get 180 bond angles, 180 degree bond angles. Okay? Well, if this thing loses its planarity, what happens to these bond angles? Well, there, we lost some planarity. Ben, damn it. What happened to these bond angles? They got smaller. Now, the organic chemists have a nice name for this, at least as I see it, because college students usually remember this name with no difficulty. It's called puckering. Because they know about this activity when two people get together who care for each other. They pucker the lips and prepare for this smooching activity. Notice in the ground state, the lips are straight across. But in the excited state, then the lips are puckered. Same thing. Except this is hardly an excited state. The upshot of this is to realize, by puckering, which leads to bond angle reduction, we get the perfect bond angles for this thing. Let's take a look at a somewhat more extreme example of this. If this thing chelates, which the name of this is propylene diamine, because when you got these 3 CH2 skeletal carbons called a propylene group. Here, ethylene group. I don't care about the name. You deal with this when you get to organic class and talk about nomenclature. Okay? 720 degrees contained within if we treat this as a planar surface. Well, if we played the arithmetic game, what we just did there, when we treated this as a planar surface, now you'd have 720 minus 90, where the coordinated metal line is to be found, divided by 5. Do the arithmetic. What do you get? Well, what do you get? Not that difficult, is it? 720 less 90 is 630. What's 630 divided by 5? How much?
126.
126. 126. All right. So I took our ethylene diamine model and I tangled it up in my microphone cord. And I added a CH2 group. Okay. Now we got 3 CH2 groups and of course our 2 terminal NH2 donor groups. Okay. Because of this free rotation about these single bonds, which are the only kinds of bonds found in this molecule, we can get these non-bonding pairs aiming at the same point in space. This is clearly not planar. Now I get an even more fancy Easter hat. Hardly planar. So this example shows again how puckering achieves the desired bond angles associated with sp3 hybridization. Given that the skeletal atoms of this ligand molecule are all sp3. Now I wrote what I said originally about these things for sigma bonding electron pairs for 3-atom ring or even 4-atom ring found not directly between the nuclei, so they're not nearly as stable. Because you would, if you had these electron pairs located directly between the nuclei of the connected atoms, you'd get extreme bond pair repulsion. Not stable coulombically. Now then, 2429. What if we had skeletal atoms which are sp2 hybridized? For example, let's do some chemistry on ethylene diamine and strip away a hydrogen atom from each of the 2 CH2 groups, converting them into CH groups. Well, if you write a Lewis picture for this thing now, you recognize at a glance by the chemistry we just described, you've converted these central carbon atoms to sp2 carbons. Bond angles? What kind of bond angles do we associate with sp2 hybridization? 120. Does it make this a better chelator or a poorer chelator? You realize if these carbons are sp3 with 190-degree bond angles, and now we convert them to sp2 carbons with 120-degree bond angles, did that make these donor pairs from the peripheral nitrogen atom get closer to each other or farther apart from each other? By converting these to sp2 carbons. What? Closer or farther apart? Farther apart. Now we did shorten this carbon-carbon bond distance somewhat, because a double bond is shorter than a single bond. But the conversion of hybridization from sp3 to sp2 winds up being a greater effect. Now then, it's also true that as soon as you convert any single bond to a bond which has got at least partial multiple electron density, in this case it's a formal double bond, then what happens to this free rotation characteristic along the axis? It's lost. So what if I go to the laboratory and instead of the molecule I have just sketched, make this molecule trans-ethylene diamine. Not diamine. Let's see, what would be the name of this? I don't know. Don't remember the organic nomenclature. But this is not ethylene diamine anymore. Now this thing can't chelate at all. Because now the non-bonding electron density from the donor nitrogen atom is pointing in different places in space. I have to make the cis version of this rather than this, the trans version. Or in this case, cis means these NH2 groups are on the same side of the double bond. And trans means they're on opposite sides of the double bond. And in organic class, you'll learn that they have better nomenclature than cis and trans for this. But I'm not going to bother with that nomenclature now. So, that gets us to question 2433. Here is the converted ethylene diamine molecule, where we no longer have a carbon-carbon single bond, but instead have a carbon-carbon double bond, and we've seen the problems that result if we're going to consider this as a chelating ligand. Well, what about going to the laboratory and stripping away more hydrogen from the central carbon atoms and make this molecule? What do you think about the chelating ability of this stuff? I trust at a glance you recognize that for any question of this nature, what do you do to wrestle with it? Draw pictures, Lewis structures. You don't have a choice. Same thing that we've said time and again. There is no more important property of a species than its structure. Now the carbon-carbon structure is that of a triple bond. How are these carbon atoms hybridized now? sp. What kind of bond angles? 180 degrees. Can this thing chelate? That's impossible. There's no way in the world the non-bonding pairs from the peripheral nitrogen donor atoms can aim at the same position in space. I mean, this leads to something I asked you to think about on bonus quiz number 3, if until now you haven't thought about it previously. As you increase the p character of a hybrid, what do you do to bond angles? SP 180 degrees, SP 2 120 degrees, SP 3 109 degrees. So you're going to also find out that in some organic classes, if the organic faculty teaching the class are of a mind to play this game, when I deal with these triangle rings and want to talk about hybridization for the skeletal atoms of this ring, given that these ring atoms are period 2, they cannot show hybridization which contains any orbitals other than s and p. So they're going to play a game. And if my memory's right, they'll call those skeletal atoms, from a hybrid standpoint, for the 3-atom ring, sp6. It's an arithmetic game. Remember, as we increase p character, we're shrinking bond angles. So they're going to mix in enough p character until you get a hybridization that corresponds to 60-degree bond angles. That's all they're doing. Now, just for fun, if I imagine an sp6 hybridized atom from period 2, like the 2 carbons and a single oxygen atom in this epoxide ring. Well, this 3-atom ring. sp6, okay? In forming this hybrid, will I have used all the s orbital? If I'm going to call the hybrid scheme for these ring atoms sp6, will I have used all the s orbital to form this hybrid? What do you think? Oh, let's go back to fundamentals. In period number 2, in any period, how many s orbitals do you find? In any energy level. In any energy level, how many s orbitals do you find? How many? You did this? Now put it to use. How many s orbitals can you find in any given energy level? Energy level 1, energy level number 2, energy level number 3, energy level number 4. How many? How many? 1! 1s, 2s, 3s, 4s, 5s. How many p orbitals do you find in in a given energy level? 3. Because a p sublevel is a package of 3 orbitals. But in energy level number 2, there is not more than one 2p sublevel. In energy level number 3, there's not more than one 3p sublevel. How many d orbitals can you find in energy level? 5. That's it. So if I'm going to argue sp6 hybridization, and I am constructing this hybrid from atomic orbitals from period number 2, will I have used all the s orbital to make this hybrid? Yes or no?
Yes.
If I'm going to use all the s orbital, and I call it sp6, that means I used how many p orbitals? sp6. I can't use 6p orbitals, damn it, there aren't 6p orbitals there. It's a game. So I'll let you think about what percentage of the s orbital was used to create this strange sp6 hybrid. Because this is just a percentage thing. What you see in sp6 hybrid, you're looking at an orbital which is 1/7 s in character and 6/7 p in character. That's what you're looking at. But if you use all the s orbital, then sp3 is the max you can do. Because there's only 3p orbitals there. So if you call it sp6, you can't have used all the s orbital. All right? I told you about this goof. Now, one more issue, which is a stereochemical issue, that of steric crowding. This relates to stunts that college students like to pull. How many college students can I get into a phone booth? How many college students can I get into a Volkswagen Beetle?
I think 10.
More than 10.
More?
Yeah, college or both.
Well, if they're really tiny college students, who knows how many? But clearly, for a phone booth, you're not going to get 300 college students in there. You just can't put two material entities in the same space that's available to allow one material entity to be there. You can't do that.
What if they attended clown college?
Attended what?
Clown college?
Clown college?
Yeah.
Hell knows who knows what they can achieve. Then they'd be orbitals, because orbitals are imaginary. They can put 1,000,000 of them in there. Like sp6. Just a game. A game we employ because it assists us to understand the chemistry of the species in question. An example of steric crowding. This is a stable octahedral complex of iron in a +3 oxidation state, an anionic complex. Hexafluoroferrate anion. And I've decided I'm not going to bother with nomenclature of coordination complex. We don't have to bother with that. Just deal with formulas. Formula is what counts the most. As opposed to hexiodoferrate. Can't make this. Now, iron in a +3 oxidation state, that's a pretty small species. You've already recognized when you take an atom, turn it into a cation, you observe rather severe shrinkage. But I-, whoo-hoo, that's a big guy. There's no way you can pack 6 I- ions around a tiny Fe3+ ion and have all the I- be in simultaneous contact with that central Fe3+. The I- are too big. They push each other out of the way. I asked you about this before. First I asked you how many BBs you could glue to a basketball. And you say a hell of a lot. I agree. But how many basketballs can you glue to a BB? 2, that's it. Can't get more than 2 basketballs glued to a BB because now the basketballs sterically hinder each other. They block each other from being glued to the BB. Same thing here. Now it's also true that you can't make this because if you mix I- with iron plus 3 in a water solution, in short order fashion you'll see the development of a purple-brown insoluble material. I mix iron plus 3 in water solution, which will be not necessarily hexacyl iron plus 3, unless the iron plus 3 molarity is quite high. But we'll consider it as such. I mix this with I-. Okay? And some non-reactive anion for the original iron plus 3 containing stuff like nitrate ion. I mix this with I- in water solution. In short order fashion, I see the development of a brown-purple insoluble material. What do you think this brown-purple insoluble material is?
FeI3.
But I'll give you a clue. If you did assignment 7 in 45 laboratory, you made some of this solid. Remember assignment 7 in 45 laboratory, not 46 laboratory, but 45 laboratory? Solutions? Remember the, pardon me, wrong experiment. Assignment 5, part 1 on fundamental aspects of redox chemistry. You remember investigating the relative oxidizing powers of the halogens in regard to the relative reducing power of halide ions? Remember doing that? Bromide's a stronger reducer than chloride. Iodide's stronger reducer than bromide, which in turn tells you that the bromine molecule is a stronger oxidizer than the I2 molecule. And of the halogen molecules, nothing's better than fluorine as an oxidizer. If you mix these two together, you get this stuff. Which is the other reason why you can't make this stuff. And there's another limitation on this chelation phenomenon. To my knowledge, you cannot make chelate complexes, which are composed of chelate rings that are in excess of 8 atoms. Now the chelate ring itself becomes a monster. And this chelate ring, because of its bulkiness, even if you only try to make one chelate ring, the bulky atoms and groups of which the chelate ring is composed start bumping into the other ligands which are in the first coordination sphere. You wind up not being able to make this stuff. So not only for chelate coordination chemistry, we got a limitation on number of atoms in the ring from few atoms standpoint, but now from an upper limit number of atoms in the ring standpoint. Now last stuff. Valence bond theory for coordination chemistry. For the most part we've already done this. That's why I'm not of a mind to spend much time with this. We did it at the tail end of chapter 23. When we told you, for example, about a material like this. Told you that it's diamagnetic. As soon as you know that stuff is diamagnetic and you know that it contains nickel in a zero oxidation state, then you can recognize what the overall valence electron structure looks like for coordinated nickel and nickel tetracarbonyl, which allows you in turn to recognize that the nickel is sp3 hybridized and recognize that this stuff is tetrahedral. That we did at the end of chapter 23. So, here are two four-coordinate complexes of nickel in the +2 oxidation state. 4 chloride ion ligands, so if the total complex charge is -2, then nickel must be +2. In fact, the only common positive oxidation state which nickel shows in its chemistry is +2. Same thing here. We talked in brief about cyanide ion and its liganding capabilities previously because it's very much like carbon monoxide. When this thing behaves as a ligand, it uses non-bonding electron density strictly from the carbon atom end. Carbons of lower electronegativity, and formal charge analysis shows you the carbon is more minus than the nitrogen. With the minus formal charge, zero formal charge. You think cyanide ion is a quite strong ligand compared to chloride ion? We did this stuff before. Regarding coordination chemistry, this thing is great. This thing is pretty feeble, but it does complex. Because when this thing complexes, you still got 1, 2, 3 residual non-bonding pairs on a donor atom, which can result in repulsion with metal, coordinated metal d-electron density. Valence d-electron density. Here, no such effect. Not only is the donor atom a better donor atom than chlorine based on electronegativity, after this thing complexes, you don't have any residual non-bonding electron density on the donor atom. So you don't have any repulsion effects with metal d-electron density for the coordinated metal. So I'm going to tell you that this stuff is paramagnetic and this complex is diamagnetic. With that information and no other information, I want you to tell me hybridization for nickel and complex geometry for each. Hybridization of the coordinated metal, which is nickel +2. And complex geometry. Now, in playing this game, what are you doing first? You realize that to play this game and win, you've got to construct one of these valence orbital energy level diagrams and populate it with the electrons that are part and parcel of the valence environment of the coordinated metal, just like we did at the end of chapter 23. How many valence electrons for nickel +2 ion all by itself? 8. What are these 8 valence electrons? SD mix, SP mix, what are they? All d electrons. So here I've written an energy level diagram which illustrates all the possible valence orbitals of a first row transition metal. Surely shows you why these things are marvelous Lewis acids. There's no way in the world you're going to fill up all these valence orbitals, so they're always going to have these transition metals, be they ionic or atomic, they're always going to have an abundance of empty valence orbitals to permit them to be part and parcel of the coordination phenomenon. All right? Each contains nickel plus 2 oxidation state, so D8 nickel. Paramagnetic. 1, 2, 3, 4, 5, 6, 7, 8. Because if we pair these two electrons, diamagnetic. Because remember, these ligands supply electrons strictly as pairs. When the ligand gets involved in interaction with a metal ion, there's no addition of electrons on a one-at-a-time basis to the empty valence orbitals of the metal. Right? The electrons supplied by the ligand come in strictly as an electron pair. So if there's any paramagnetic character, if there's any paramagnetic character exhibited by a complex, unless you've complexed unusual ligands which themselves are paramagnetic, and that's rarely the case, then the paramagnetic character has got to be attributed strictly to the electron configuration of the coordinated metal itself. All right? 4 ligands, 4 bonding electron pairs. Maintaining paramagnetic character. Hybridization sp3. Geometry for this stuff, tetrahedral, done. Now, based on the observed diamagnetic nature of tetracyanonickelate 2, that's the name of this stuff, this can't be the total valence electron configuration, because this corresponds to diamagnetic character. So let's take away these electron pairs, put back the orbitals. And recognize, for starters, that the nickel valence electrons, the electrons which are formally part and parcel of the nickel valence environment exclusively, got to be all paired, because this thing is diamagnetic. But again, we got 4 ligands. This is 4-coordinate nickel, just like this is 4-coordinate nickel. Well, what orbitals do we now have available for occupation by the non-bonding pairs supplied by the 4 cyanide donors, each of which become bonding pairs on coordination? Tell me the hybridization scheme. DSP2. Tell me the geometry. Square, planar, or square? All right. So we'll finish with one more game. Since this thing is square, there's nickel 2 at the center of the square. Here's a cyanide ligand, and a cyanide ligand, and a cyanide ligand, and a cyanide ligand. And since it's square, I'm going to imagine that this square lies in the XY plane. All right? The question is, if this square is imagined by us to lie in the XY plane, lies in the XY plane. Oop. Question. Which p orbs and d orb are used to make the dsp2 hybrid. If this complex lies in the xy plane, which p orbitals and d orbital are used to make the dsp2 hybrid. Now then, have you seen this model before? What is this a model of? A family of p orbitals, a sublevel of p orbitals. One with its lobes oriented this way. What's this direction? X. This is X. An up and down p orbital. Now in chemistry class, what's the up and down direction? Z. So by default, this p orbital with one lobe aiming at you and the other lobe aiming at me is on the y-axis. All right? Which of these p orbitals? If this is px and this is py, which of these p orbitals are used to construct this dsp2 hybrid if the xy plane contains this complex? Which p orbitals? X and Y. P sub X and P sub Y. All right? Which d orbital? Now we haven't spent much time paying attention to d orbitals, but the pictures are in the book, and here are the models. This is a special d orbital in that its lobes are skewered by the axes, right? And this d orbital that I hold you lies in this plane. What is this plane? The xy plane. And these lobes are skewered by the axis, which means for the complex and its spatial orientation, x-axis, y-axis. Do these orbital lobes aim right at the ligands? Well, if you want best overlap, will you not have the orbital lobes aiming right at each other? So you already know which d orbital is used to make this hybrid, don't you? It's this thing. What do you think the label is for this d orbital? Do you know what it is? I'm just curious. It's dx squared minus y squared. It's a mathematical label. Never mind that. Take note, if you will, that this d orbital also has its lobes lying in the xy plane, but these lobes are between the axes. So given that we've chosen to imagine that the ligands lie on the xy axes respectively, then this d orbital would not give us nearly as good overlap as the x squared minus y squared. This d orbital has its lobes in this plane. This plane is YZ. No good, because how are we going to make bonds with these cyanide ion ligands that are on the x-axis? This d orbital lies in the XZ plane. So how are we going to make bonds with the cyanide ions that lie on the y-axis? And the remaining d orbital is this thing, which is rather unique in its shape. But interestingly enough, these 5d orbitals are all absolutely equivalent probability regions for finding electrons and electron density in d orbitals. This thing is called dz squared. Z square is obvious because the main lobes are on the z-axis. But it has this nice donut for a fancy belt. I like to call this fancy belt a cummerbund. If boys don't know what cummerbunds are, they usually learn when they get involved in this thing called betrothment. nuptialization, because the wife-to-be will insist that future hubby is attired quite nicely, so they have to wear cummerbunds. So did I. Now, one more thing. I told you these are all absolutely equivalent probability regions. But this thing has a shape which is clearly different from the rest of them. All look like three-dimensional four-leaf clovers. Okay? Now look at this thing. And let me hold this x squared minus y squared d orbital like this. Do you see the identical nature of the lobes of this d orbital when I hold it like this? Now what happens when I spin this? What kind of shape do these lobes generate? The cummerbund. That's it. So I'll leave you with one remaining thought. Not only for happiness and success, but for chemistry that you may consider if you go to organic class. What is this? It's a benzene ring. You've seen this. It's considered by organic chemists to be essentially the parent molecule for exhibition of resonance. Now, what we're curious about is what happens to this benzene ring if we take tonight's exam and we make a perfect score. Well, as a consequence of that, we might treat this benzene ring with pop, if you like sody pop, lemonade, if you like lemonade, if you like me, you might do some of this stuff, Heineken, and then our benzene ring looks like this. And that's all.